In this lesson, we will learn that wave-particle duality also applies to matter. We will also learn about the Heisenberg Uncertainty Principle, which is an important consequence of wave-particle duality. In earlier lessons, we saw that towards the end of the 19th century, the behavior of light had been successfully explained in terms of electromagnetic waves. But then, observations like the photoelectric effect and Compton scattering could only be explained if light were thought of as consisting of massless particles, which are now called photons. Thus, we say that light exhibits wave-particle duality. The equation relating momentum and wavelength is given by P equals h over lambda, where h is Planck's constant. In this equation, P is the momentum of the photons. Lambda is the wavelength of the wave that is associated with the light. We say that the momentum is inversely proportional to wavelength. Momentum is something that had been associated with particles with non-zero mass, not with light. The classical definition of momentum is P equals mv, where m is the mass and v is the speed of the particle. The universe tends to be symmetrical, so Louis deBroglie hypothesized that if light, which was then considered as waves, were found to exhibit particle-like behavior, then maybe particles that make up matter could also exhibit wave-like behavior. Given that the momentum of a photon p is equal to h over lambda, it's easy to see that lambda is equal to h over p. deBroglie hypothesized that for particles of matter, the wavelength is also given by h over p. However, for a particle with mass m and speed v, the momentum is m times v. So we can also say that the wavelength of a particle of matter is equal to h over mv. Note that mv is the momentum only for particles of matter. That is, particles with mass, not photons. Although photons are massless, they have non-zero momentum. Also, as the speed of a particle approaches the speed of light, we need to apply a relativistic correction. We must use the relativistic mass, which is equal to m naught, divided by the square root of 1 minus v squared over c squared. M naught, the rest mass, is the mass of the particle when it's not moving. V is the particle's speed, and c is the speed of light. Calculate the momentum and speed of an electron with a wavelength of 3 nanometers. The momentum p is equal to Planck's constant divided by the wavelength lambda. We are given the wavelength is 3.0 nanometer. We just multiply 3.0 by 10 to the negative 9 to express the wavelength in meter. Planck's constant is 6.626 times 10 to the negative 34 joule second. Plugging the numbers, we get 2.2 times 10 to the negative 25 kilogram meter per second. Note that the unit for momentum is a unit of mass, kilogram, times a unit of speed, meter per second. Since momentum is mass times speed, we can calculate speed by dividing momentum, which we now know, by the mass of an electron. The rest mass of an electron is 9.11 times 10 to the negative 31 kilograms. You'll be using this number a lot, so it's good to memorize it. It should be easy to remember 911. Plugging in the values for the momentum and mass of electron, we find that the speed of the electron is 2.4 times 10 to the 5th meter per second. Note that this number should not exceed the speed of light, which is 3 times 10 to the 8th meter per second. If it does, or even if it's less but happens to be significantly close to the speed of light, we need to do a relativistic correction for the mass. Experimental verification of deBroglie's hypothesis came in 1927 when Davison and Germer fired a beam of electrons on a nickel crystal. They found that the scattering of the electrons showed a diffraction pattern. Diffraction is a phenomenon associated with waves. Diffraction of a wave is readily observed when the wavelength is comparable to the gaps between the obstacles encountered by the wave. In this case, the obstacles are the atoms in the crystal. In Davison and Germer's experiment, the wavelength of the electrons used are of the same order of magnitude as typical distances of neighboring atoms in a solid, which is around 1 to 5 angstroms. Calculate the wavelength of an electron accelerated through a potential of 100.0 volts. We can calculate the momentum of the electron from its mass and kinetic energy. The momentum is equal to the square root of 2 times the mass times the kinetic energy. An electron has a mass of 9.11 times 10 to the negative 31 kilogram. If the electron is accelerated through a potential of 100 volts, then assuming it starts from rest, its kinetic energy becomes 100 electron volts, or 1.602 times 10 to the negative 17 joules. Plugging in the mass and kinetic energy to the formula for P, we get a momentum of 5.403 times 10 to the negative 24 kilogram meter per second. Determining the wavelength is a matter of dividing Planck's constant by the momentum. We get 1.226 times 10 to the negative 10 meter, or 1.226 angstroms. This wavelength is comparable to the typical distance between neighboring atoms in a solid, and we would expect that a beam of electrons accelerated through a potential of 100 volts to be diffracted when it encounters a solid. If you're wondering where the formula for P comes from, here's a simple derivation. Kinetic energy is 1/2 times the mass times the square of the speed. Multiplying the right side by m over m is like multiplying it by 1, so it would still be equal to the kinetic energy. We can combine the two m's in the numerator as m squared, and since mv is equal to p, m squared times v squared is equal to p squared. Thus, the kinetic energy can also be expressed as p squared over 2m. If we rearrange this equation to solve for p, we get P equals square root of 2 times the mass times kinetic energy. Calculate the wavelength of a 0.20 kilogram ball moving at a speed of 1 meter per second. Can we expect to observe wave-like behavior for this ball? The deBroglie wavelength lambda is equal to Planck's constant h divided by the momentum p. We calculate the momentum from the given mass and speed and get 0.20 kilogram meter per second. Plugging this and Planck's constant into the expression for lambda, we find the deBroglie wavelength to be 3.3 times 10 to the negative 33 meters. So, do we expect to observe wave-like behavior? Well, only if the ball has to go through obstacles that are about 10 to the negative 33 meters apart. For context, a typical atomic nucleus has a diameter of about 10 to the negative 14 meters, which is much larger than 10 to the negative 33. So the answer is no. We do not expect this ball to exhibit wave-like behavior. 10 to the negative 33 meters is a very short wavelength. This is generally true for everyday macroscopic objects that we encounter. These are objects that are adequately described by Newton's laws of motion. Wave-particle duality tends to be important only in the world of the very small. For very small particles like electrons, the mass is small enough that the wavelength can become large enough to be detectable. Ernest Rutherford's alpha scattering experiments established that an atom consists of charged particles. A positively charged particle in a very small region called the nucleus, and negatively charged electron in a much larger but mostly empty space around the nucleus. Classical physics suggests that such a structure for an atom could not possibly be stable. Negatively charged particles are known to attract positively charged particles. A negatively charged electron will be pulled towards the positively charged nucleus, regardless of whether it is initially moving towards the nucleus or away from it. Therefore, an electron should crash into the nucleus in no time. It is possible for two particles attracted to each other to not crash into each other. For example, the Moon and Earth have gravitational attraction between them, but the Moon is in a stable orbit around the Earth. However, the problem is that a charged particle emits electromagnetic radiation and loses energy if it is accelerating. An electron in an orbit around the nucleus is accelerating and will therefore emit electromagnetic radiation. This means that it will be losing energy as it orbits around the nucleus. It will in no time be expected to crash into the nucleus following a spiral motion. Niels Bohr assumed that there are stable or allowed orbits around the nucleus where an electron would not crash into the nucleus. With this assumption, he was able to successfully explain the observed emission spectrum of hydrogen in terms of electrons hopping from one allowed orbit to another. However, he was not able to explain why or how any orbit can be stable. deBroglie's idea of wave-particle duality being applicable to electrons provides a justification for Bohr's allowed orbit. Imagine superimposing a wave associated with an electron around an orbit. For example, imagine this is an orbit, and this is the wave with wavelength lambda. If the radius of the orbit is r, then the circumference is 2 pi r. The orbit would be stable if its circumference, 2 pi r, is a multiple of the wavelength lambda. Multiple of lambda is n times lambda, where n is a counting number. For this orbit to be stable, the circumference should be equal to lambda, or 2 lambda, or 3 lambda, and so on. In the example shown here, the circumference is 3 times lambda. We get a standing wave due to constructive interference, so we say that the orbit is stable. This only happens when the circumference is a multiple of lambda. Otherwise, the wave destructively interferes with itself and the orbit is unstable or not allowed. A consequence of the wave nature of particles is that it is not possible to simultaneously determine the exact location and momentum of any particle. This statement is called the Heisenberg Uncertainty Principle. Mathematically, the principle is typically written as delta x times delta p sub x is approximately equal to h, where h is Planck's constant. Delta x is the uncertainty in position, and delta p sub x is the uncertainty in momentum along the x-axis. The more precisely we can measure the position, the smaller delta x is. Similarly, the more precisely we can measure the momentum, the smaller delta p sub x is. When the product of two quantities is equal to a constant, it means that they are inversely proportional. The smaller the delta x is, the bigger delta p becomes. This means that the more we try to pinpoint the location of a particle, the less certain we can be about its momentum. Similarly, the more we try to precisely determine the momentum, the less certain we can be about its position. If we use standard deviation to express uncertainty, the uncertainty principle is given by the expression delta x times delta p is greater than or equal to h bar over 2. Note that for brevity we use delta p here instead of delta p sub x. We actually mean delta p sub x. The symbol h bar is quite commonly used in quantum mechanics, so you should be familiar with it. It's just Planck's constant divided by 2 pi. Its value is 1.055 times 10 to the negative 33 joules second. The uncertainty principle, which is a consequence of wave-particle duality, which is based on experimental observations, implies that any attempt we make to predict the trajectory of an electron spiraling into the nucleus is not acceptable. Knowing the trajectory of a particle means precisely knowing at specific times where it is, how fast it's moving, and in which direction. That would be a violation of the uncertainty principle. Strictly speaking, Newton's laws of motion are not correct, but it's perfectly fine to use them to describe the macroscopic world. We can think of them as very good approximations if we're dealing with big things. They fail if applied to the world of the very small. The speed of a 0.15 gram bead is known to within 1 millimeter per second. Estimate the uncertainty in the position. The uncertainty principle says that the product of the uncertainty in position, delta x, and the uncertainty in momentum, delta p, is greater than or equal to h bar over 2. H bar is equal to Planck's constant divided by 2 pi and is equal to 1.055 times 10 to the negative 34 joules second. If we want to estimate the uncertainty in the position delta x, we simply divide both sides by delta p. This gives us delta x equals h bar divided by 2 times delta p. In this question, we are given the uncertainty in the speed as 1 millimeter per second. This is equivalent to 1.0 times 10 to the negative 3 meter per second. Since momentum is equal to mass times speed, and we are given that the mass is 0.15 grams, or 1.5 times 10 to the negative 4 kilograms, we can calculate the uncertainty in momentum, delta p, as mass times delta v. Plugging in the mass and delta v, we get delta p equals 1.5 times 10 to the negative 7 kilogram meter per second. Finally, plugging in this value of delta p and h bar in the expression for delta x, we find that the uncertainty in position is at least 3.5 times 10 to the negative 28 meters. A beam of electrons with deBroglie wavelength lambda would behave just like light that has the same wavelength. One phenomenon that demonstrates the wave nature of light is single-slit diffraction, which is illustrated here. We shine light through a slit. As illustrated here, the width of the slit is labeled A. If we put a screen behind the slit, we see a pattern of bright and dark bands, instead of just one bright spot aligned with the slit. We can explain the pattern in terms of constructive and destructive interference of waves that were bent when they emerged from the slit. What happens if we make the slit smaller? The image on the screen spreads out more. So how does this illustrate the uncertainty principle? Well, if we were to use an electron beam instead of light, the brighter spots would correspond to where more electrons hit the screen. Making the slit smaller essentially means that we are trying to more precisely determine the location of the electrons. The spreading out of the image on the screen means that there is greater uncertainty in the momentum of the electrons. Estimate the uncertainty in the momentum of an electron fired through a 100 picometer slit. The product of the uncertainty in position, delta x, and the uncertainty in momentum, delta p, is greater than or equal to h bar over 2. H bar is equal to Planck's constant divided by 2 pi and is equal to 1.055 times 10 to the negative 34 joules second. If we want to estimate the uncertainty in the momentum, delta p, we simply divide both sides by delta x. This gives us delta p equals h bar divided by 2 times delta x. In this question, we are given the uncertainty in the position, 100 picometers. This is equivalent to 1.00 times 10 to the negative 10 meters. Finally, plugging in this value of delta x and h bar in the expression for delta p, we find that the uncertainty in the momentum is at least 5.27 times 10 to the negative 25 kilogram meter per second.